polymer science at Stellenbosch University, where she focused on water treatment and the removal of heavy metals using polymer nanomaterials. Currently, Dr. Boats works as the electron microscope analyst for the Central Analytical Facility in Stellenbosch University, South America. You're welcome, Dr. Alicia.
Thank you. Should I switch off my video just for the internet to make sure that it's not lagging or anything like that? Is that all right? I will switch off the video. All right.
Yes.
Thank you very much for the warm welcome. I appreciate it so much. I'm really excited to be talking at this conference and spending my time among such distinguished people and like-minded polymer scientists and chemistry enthusiasts. Thank you very much. So yes, my name is Alicia Boeters. As you've already mentioned, I've done my PhD in chemistry and polymer science, but I'm also an analyst at the Electron Microscope at the Central Analytical Facility in Stellenbosch University. So today we'll be just talking about scanning electron microscopy for polymers specifically. You can let me know if my internet is lagging or if there's anything that goes wrong. If I speak too fast, you're welcome to interrupt me. So firstly, let's just continue with this slide. Right, so just a brief outline. We were talking about the electron microscope and a brief history of it and how it started. And then why do we use them? And then the components of SIM, as well as the principles of how scanning electron microscopy works. And then we'll carry on and talk about the energy dispersive X-ray analysis, which is sometimes a crucial part of analyzing and characterizing a polymer. And then we'll talk about polymers in SIM specifically and continue on with how we sample prep polymers and how we prepare them for SIM. Then we'll end off by just talking about how SIM has grown, the technology that is available currently, and also how that can be useful for polymer analysis. So the electron microscope, a brief history. So just to quickly outline how the SIM came about and how it has grown. We started in 1935 with Max Knoll, he created the concept of SIM, and he was a crucial part of how SIM came about. Then we moved on to 1938, where Manfred van Ardenne actually helped improve the SIM by adding scanning coils to a transmission electron microscope, creating the first scanning transmission electron microscope called SIM. So there was a lot of improvements done by a lot of people, but these are the most common and most popular people that's known. So the first micrograph that was analyzed with the SIM was actually a zinc oxide crystal. And this was imaged at 23 kilovolts at 8,000 times magnification with a spatial resolution of 50 to 100 nanometers, which is amazing to think about how long time ago that was. So, but unfortunately, scanning such a sample took 20 minutes back then. Where it now happens instantaneously. So it took 20 minutes because they had to manually, mechanically move the stage in synchronization with the beam. So it wasn't so high tech, of course, back then. But yes, moving on, we then go to 1953 with Dennis Macmillan and his group, and they actually improved the SIM to a way that we now would recognize it with the 3D imaging and the characteristic view that we see when we use SIM today. And in 1955, Ken Smith and Charles Oatley, also very distinguished people in the SIM community, they had students called Wells, Everhart, and Thornley, and they made improvements to the secondary electron and backscattering electron detectors by adding scintillators to convert electrons to photons. Now, I've added the very popular article written in 1960 by Thornley and Everhart for anybody who would like to go and read about that afterwards, because it's a very interesting read, and anybody interested in scanning electron microscopy will find this very interesting, since this is one of the most popular articles, and it's very, very old. So it's very like in the archives and still very interesting. So next, why do we use SIM? So there's no other instrument with the breadth of application in the study of solid state materials that rivals that of SIM. SEM can achieve resolutions under 1 nanometer. It's also, the polymer sample preparation for SEM is really not complex. It's very user-friendly. And you can achieve a high depth of field, which means that you can actually, for tall samples and large samples, you can still see a large portion of the specimen and get it to focus. And you can actually have a nice overall visual of your sample. Then you can also achieve high resolution at very high magnification, which is rather amazing. And then the SEM controls, like I said, even the software nowadays is extremely user-friendly. So with the right training and extensive practice, you can actually have anybody operate a SEM, because there are so many cautions and the stuff in place that will prevent any user from harming the instrument. And then qualitative and quantitative analysis are basically the key why we are using SEM, especially for polymer analysis. So you can get the topographical surface texture analysis, where you can see the fine textures and details of your surface of the sample. And then you can also see the morphological analysis, where you see the size and the shapes of particles, and also establish whether these particles are the shapes and sizes that you were hoping for. Then chemical composition are usually what we're interested in when we're trying to analyze our sample. So we are interested in what the elements are within our sample, and we also want to identify whether some of the samples have been contaminated, or whether elements that we were trying to introduce into the sample are there or are they missing. So that's also very useful too. And then finally, crystalline structure arrangement. So to view our sample and to make sure that what we are getting or what we are hoping to see are actually there. Okay, next slide. So this is just a picture of my previous work from my master's and my PhD thesis. So on the top left, you can see where it's marked A. These are fibers. Now, I wanted to call them nanofibers, but they are definitely not a nanoscale. And with the help of SEM, I was actually able to establish that. So this was electrospinning gone wrong, unfortunately. So these fibers were a bit beaded and agglomerated, but that was useful for me to adjust my electrospinning method and then improve on the electrospinning and the nanofibers. Then B, you can see, if you look at the magnification, it's at a lot higher magnification, and the scale bar indicates that these are actually in some form of nanoscale range. Not all of them, but there are some. And also you can see the precipitate, that powdery white precipitate is zinc. Now SEM actually points out these finer details within the fibers. And this was also just for me to see whether this can act as a filter, a membrane filter or something, to remove heavy metals from water. And that was a good indicator of that it does its job. And then on the right-hand side, you see a nanocomposite. And this was also a very good a replication of how you can see fine details within a composite itself. We were trying to establish whether fiber mats melt pressed between two EVH films will be able to still retain some fibrous texture and some fibrous components. And we did see some fibers in there, and you can actually see the layers as you go closer into the sample. So this is also all just tools that we can see how useful SEM can be in just the normal sense of it, without too much sample preparation. So for the next images, this is also just an example, just to show how the different types of scanning electron microscopy and transmission electron microscopy can help you in your endeavors for your research. Here we have chitosan nanoparticles on your left, and other type of particle from a student called Reiner van die Kerk, and he used SEM because his particles was far more in the nano range and very, very small in feature. So we had to use scanning transmission electron microscopy in order to visualize that. So that is the one limitation with scanning electron microscopy compared to scanning transmission electron microscopy. So if your samples are extremely small, then you have to unfortunately use SEM. If you want to get a very nicely focused, high resolution, high magnification image. So if everybody can still hear me, I hope that's fine. If you can't, then just let me know. All right, so the components of SEM. So I won't try to talk your ears off your head, but there's a few components of SEM that's very important to mention. as you can see on the picture on your right, we start with the vacuum chamber and we go to the electron gun and then we go down to the sample chamber. So the first thing that's very important of SEM is the vacuum. This is typically between 10 to the minus 5 and 10 to the minus 11. And this is used to avoid any collisions of the electrons that is created from the electron source and to avoid the collisions with other molecules or contaminants within the chamber or in the column. So moving on to the electron source, we have a thermionic emission. So it's either called thermal or sometimes called thermionic emission. So this is usually comprised of a filament, which is heated by application of the electric potential between the filament and anode. As you can see on the picture on your right-hand side, you have your anode there. And the filament is basically shown in the picture above you. You can get two types for the thermal emission, which is a 1 and 2. So the first one is a tungsten filament. Let me just show this here. So tungsten filament, and you have your low vacuum, short life type of filament there. Unfortunately, it doesn't bode well to use this type of filament for high resolution SEM. But then you have your solid state crystal, which is also mainly in it's comprised usually of cerium hexaboride or lanthanum hexaboride. So this gives you a better brightness and it gives you a much longer lifetime compared to the tungsten filament. But unfortunately, it requires a higher vacuum and it costs a lot more. Then we have the field emission. This is another type of emission. The field emission is usually called a cold field emission. And it's a strong electric field, which is applied between aperture anode and the tips to create electron tunneling. So it's a sharp, I don't know if you can see my mouse, hopefully you can, but it is a sharp crystal tip that's less than 100 nanometers. It uses a high vacuum, but that is only to keep the tip clean, as we've mentioned earlier. And then the beneficial thing about this sharp crystal tip is that it can make a narrower beam and the filament lasts much longer. So another component of SEM that's crucial is the lenses. So moving down to the condenser lenses, there are a series of them that focuses the electron beam as it moves from the source down to the column. If the beam is narrower, the spot size will be smaller. So the beam narrowness and the spot size is directly proportional. So when it reaches the sample surface, the spot size will be small if the beam is much narrower. So then there are the scanning coils, which we mentioned in the brief outline in the history. These coils allow the beam to be scanned over the sample in a raster-like manner from in an X and Y axis, so up and down and left to right. So this is a picture here in the bottom right, across from the sample chamber, that allows you to see what is meant by a raster scanning manner. Then we have the sample chamber, and that's the final most crucial part before we get to the detectors. So the samples are loaded into this chamber, and this chamber is usually evacuated using a vacuum pump, and you can rotate and tilt and move the stage up and down and sideways, and that's all very beneficial depending on the sample that you have. So then we come to the detectors. So we have various different detectors which are quite crucial for the analysis of the electrons that comes from the sample and from the electron beam. So these distinguished detectors are secondary electron, backscattered electron, and characteristic X-ray detectors. So the first one is the SED, which is a secondary electron detector, and these secondary electrons are acquired from inelastically scattered electrons close to the surface of the topographic surface of the sample. And this is very useful if you want to see the surface texture, like I've mentioned earlier. Then you have the backscattered electron detector, and this detects the elastically scattered electrons from atoms much deeper in the sample. So that also just helps with the analytical side of the sample itself, where you can distinguish between the types of materials in your sample. I'll get to that in a little bit more detail in the next few slides. So the principles of SEM. So unlike modern light microscopes that uses light, a scanning electron microscope produces images of a sample using a focused electron beam that scans over a sample. So electrons have a much shorter wavelength than that of light, and that helps with the high resolution that we get from tiny features of our sample. So several signals are produced by the incident beam hitting the sample, which are detected by designated detectors. The elements with a higher atomic number will have a brighter appearance. Now, when I say this, that's what I meant when I said the backscattered electrons can help you distinguish between the types of materials in your sample. So as the atomic number increases, the brightness of the material itself will increase and appear lighter compared to the rest of the materials. So we have the various types of signals shown on the right in the image. So first we have the algo electrons. And these are very interesting electrons. They come from just the electron from the higher orbital exiting the atom orbital, and then another higher electron needs to fall back into the place of that one. So it's just an interesting phenomenal type of algo electron, but not always used for the analytical side of the SEM. But then you have the secondary electrons, which is the one we focused on for topographical analysis and surface analysis. And they're the backscattered electrons, like I mentioned. They are for more detail in terms of distinguishing between the materials. And then the characteristic X-rays, which are what I'll be talking about next, they will help with the elemental analysis of your sample. Then the continuum X-rays are just background mostly, and there's a lot of, there's other details there that we can talk about, but I won't be going into that in much detail. And then obviously the fluorescent X-rays, they are characteristically used for XRS analysis. Then moving on, the maximum resolution depends on two factors, but these are the two main factors, just to make it more simple. So usually the electron spot size are a crucial part of improving the resolution, and then interaction volume of electron beam with the sample, which means basically the beam strength also impacts the resolution of the sample, of the analysis and the image. So the principles of energy dispersive X-ray analysis. So this is the X-ray signals that I was talking about earlier. So on your right, I've added an image. It's called an EDX map. This helps with the identification of various types of elements and also separating them and making sure that you can actually establish and distinguish between the elements. And this is a color overlay, so you can choose the various types of colors and change it up and make it a very interesting picture for an article and so on. So the energy EDX, your EDX actually is used for analyzing the X-rays that are emitted from samples due to excitations of electrons in an atom caused by the incident beam. So the electrons are usually ejected from an inner shell and creates an electron hole, which is then filled by an outer shell electron, and this emits that X-ray. So the energy that's released from the higher energy electron, the outer shell, then moves to the lower energy inner shell and is called an X-ray. I hope that makes sense. But so each element has a characteristic X-ray, basically a fingerprint that you can establish which element belongs to which X-ray signal. The poor spatial resolution is usually seen, or the X-ray has a poor spatial resolution compared to backscattering electrons and secondary electrons. So you won't necessarily use an X-ray to get a nice image. That will be up to the backscattering and the secondary electrons. It is important to note that hydrogen, helium, and lithium are too light. These elements are very light, meaning they have a very low atomic number and therefore cannot be detected by using EDX, unfortunately. All right. So polymers and SEM. So specifically focusing on how polymers are useful, how SEM is useful for polymers. Polymers are typically long chains of repeating units composed of low atomic number elements. So this is, for example, carbon, hydrogen, nitrogen, and oxygen. These elements, excluding hydrogen that we've mentioned, we cannot detect, with STEM with EDX requires staining or coating to enhance contrast and give us a better visual. Polymers are extensively used in packaging, biomedical, electronic, and food industries. So that's just to mention a few. We know that polymers are crucial in almost every type of field. So it's very, very interesting. And that's why I also love polymers and polymer science. So scanning electron microscopy you can use that to study the quality of polymers, and you can study the chemical and physical properties of these materials as well. So basically, you can test anything using STEM, you can evaluate any test through STEM. So if you did tensile testing or thermal stability testing, or you were checking the miscibility or compatibility of materials, you can evaluate the effect that tensile test or thermal stability test or whatever did to your sample by using STEM and looking at the finer features, aka cracking or some type of incompatibility and so on. So if you want to check, for instance, the porosity or size or distribution of particles, and also just in general, the features that you were hoping to see, like I've mentioned, using high resolution STEM is very, very important. And and also using the correct sample preparation before you actually go for a STEM evaluation is key. If you do not do the correct sample preparation, you will impact or affect the changes that was made on your polymers through the test or through the experiment, and alter the effects and then change and introduce artifacts which will cause you to get inaccurate data or make inaccurate conclusions. So that's a very, very important sample preparation. And we'll be talking about that soon. If the areas of interest are around 100 nanometers, STEM is a safe option. But for smaller features, I've mentioned that STEM or TEM would be much better if you have very, very tiny features. SEM and STEM require different sample preparations. So I will mention that also in the next slide. Sample preparation for polymer samples. So firstly, conductivity is very, very important. I'll talk about how we can introduce conductivity in a sample soon. So first, next thing is your sample needs to be compatible in high vacuum areas. So it needs to be also very clean and free of moisture. So it needs to either be prepared in another way that you can remove the moisture from the sample using fixative, which is a fixative sample preparation method. It's usually where we would find for biopolymers or for biomedical or biological samples. So that's something that I'll explain just now. Then you have the stable, it needs to be stable under electron beam exposure. So the sample shouldn't melt or explode under the electron beam, since this is a high kilovolts and high energy situation that you are placing the sample under. And then the sample has to have a level area. It needs to have a surface that is flat and level so that you can have the best quantifiable analysis possible. It is okay if the samples sometimes have irregular levels, but then we need to make sure that we establish some sort of method that we can have the best image possible and the best analysis possible. So usually that's done via polishing or just mounting the sample in the correct way on the stub before introducing it into the chamber. Then for STEM sample preparation, it's usually very, very simple. As you can see on the picture on the right, I've indicated some methods for sample preparation. The large mount you see on the bottom, I think I can show you here. This is usually for geological samples, but sometimes for powders that you need quantifiable data for. This is also a very good way of embedding your sample in resin and then polishing it and making sure that the area is level, that you have the best opportunity to access your sample. So then it needs to be also small enough to fit into the SEM chamber. So I've crossed out this a very, very large sample that was brought to me once, just to show an example of what cannot go into a sample chamber. Unfortunately, this will bump into the lens and it will be impossible to image, or sometimes even load into the chamber. Some chambers have been made larger, some SEM chambers are larger and can fit some samples in that's oversized, but this is very uncommon. And then the most common way of loading your sample is on an aluminium stub with a carbon tape, where you just mount your sample and stick it onto the carbon tape. So electrical conductiveness is then the most important step after mounting your sample. And this is usually done to avoid charging effects. Charging effects is caused by the electron being conduced over or conduct over your sample, and not actually, it just runs over your sample and creates this very hazy, blurry effect that's horrible for imaging, and it will waste your time completely. So this is usually achieved either naturally with a sample that is already naturally conductive, or by coating the sample with carbon or gold. So for an example, we have a gold palladium alloy target that we use to coat the sample with a 10 nanometer layer. So that really won't affect your sample surface, and it won't affect any detail that you want to see on your sample. So the next one is STEM or TEM sample preparation. So sample suspensions are usually necessary. If you have a nanoparticle solution, then this is the best way of imaging them, is by dropping them on a grid. Usually there's some sort of staining that is necessary for background staining, or just to stain your sample itself. So we usually use urinal acetate or osmium tetroxide, but there are so many stains available that you can adjust this according to your sample and your needs. Then we have resin embedding, which is, like I've mentioned, also an option if you have unstable powders or some sort of sample that doesn't work and doesn't want to cooperate with the SEM chamber. And we can make a resin embedding mount and polish it and ensure that it gives you the best data. Then there's other options. When you do this resin embedding in TEM, you can actually use ultra micro-TEM. So you won't do resin embedding and have it look like the mount. Then you'll have it in a different type of resin that can actually be sliced into very thin sections, about 30 to 60 nanometers, using an ultra micro-TEM. So these ultra thin sections are then used for STEM. So you cannot use the sample needs to be very, very thin and very small to be introduced for STEM analysis. So other STEM technologies that are available for polymers. There is a lot of various types of different extensive analysis for STEM that's available. As the technology increases and the passion for STEM increases, there are so many developments and improvements done. But one that is always faithful is Cryosin. So this technique is used to image specimens in a frozen preserved state. So this is used for samples that tend to outgas and is not competent in a natural state in a high vacuum. Samples are usually flash frozen with liquid nitrogen and then introduced to the SEM with a cryo stage and kept below water sublimation in a vacuum. So this is useful for gels and oils and things that doesn't really always seem to be compatible with SEM. And there's a picture on the right that I just used as an example of a biopolymer network that was evaluated in this way. So other types that are very interesting to use are cathode diluminescence. SEM, that's an alternative technique that is used to distinguish between materials without using elemental composition. So if you don't want to do EDX, or you can't do EDX for some reason, then this is the best option. So the cathode luminescence are created with the free electrons that is caused by electron propagation through a space that allows for cathode luminescence. So the sample usually has this is usually a sample that's created. This is usually a luminescence that's created by the sample itself. So many polymers are cathode luminescent and can be distinguished based on varying wavelengths in the materials. So this picture on the right is very interesting. It's a various components of ingredients: polyester, high density polyethylene, and polyether etherimide. Sorry, and this is a very interesting way of distinguishing between these components in the specimen. So yeah, just another very interesting one. We finally have there's only one of these serial block phase SIMs available in South Africa at the moment, and we have them here with us in the Central Analytical Facility. This is a way of constructing a 3D image of your sample. So it gives you a very interesting 360 view of your sample, and it's fantastic for articles and presentations, and just getting a very, very detailed view of your sample. So A to C here on the left-hand side is a serial block phase 3D imaging of a polymer blend. And there's just the data that was used, those micro slices that was used. So showing the particle distribution in the matrix. So you can actually see I think this is iron in the sample particles that was actually distinguished in this way. So, and then you've got D, which is a 3D construction showing cracks. The red is the cracks. And this is in isotactic polypropylene that's modified with ethylene propylene rubber. So the rubber is in green. So that's a very great way of seeing the cracks and how they are distinguished in the polypropylene. And then E, the final one, is a 3D construction image of cast aluminium, iron, silicon alloy, and it's enriched with iron as well. And you can see that there's some way of they are overlaying it with color, so you can identify the various components and how they are interacting with each other. Yeah. So that's all that is. Yeah. So they're kind of also including EDX and mapping and combining these types of analysis to get a very detailed image. Yeah. So thank you very much for your attention. I really appreciate that you invited me to this conference. It was so much fun to talk to you about this. If you have any questions, you're welcome to ask me, but there's also much more detail about STEM and the things that I maybe just brushed over that you can go and visit to these links. We have a YouTube video on the Central Analytical Facebook YouTube channel, and then you're welcome to visit the website to see how you can maybe book a consultation or send some samples to us if you need them for evaluation. And then I also have a Polymer Science podcast that you're welcome to check out if you want to. Thank you.
Thank you so much.